Hey folks, okay, well we said we'd come back and look at type handling and type checking in particular, so let's spend a little bit of time going through some of the issues that we're going to have to deal with in terms of doing our type checking once we've parsed our code. So first off, the idea of our data types in general are to provide some layer of abstraction and some layer of control for the developer where they can go through and say, well, I've got these kind of vague abstract data types or types that I want to work with. So I don't want to confuse this with abstract user-defined abstract data types later on. But going through it, we want to be able to say, well, I want to work with integers. I want to work with real numbers. I want to work with strings. And you don't want the developer to have to go through and specify, well, that's going to be bit sequences like blah, 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 blah. You want to be able to specify that I've got all of these different types of data and to be able to work with them on that basis. I want to be able to support operations on these different types. I want to be able to enforce type checking perhaps, right, so that we can get compile time checking of data types, or we can get runtime checking of data types to make sure that the data values in use actually conform to the rules for the data type that I'm trying to work with. So different languages, of course, have completely different forms of data types and data type checking, and our compiler is going to have to deal with whatever that particular language specifies. So we've got the kind of abstract notion and the idea of being able to perform compile time checking and or runtime checking. And it's entirely possible that the types that we're working with also have some really close relationship to the eventual implementation of this stuff at the hardware level. If you're talking about the range of values that can be supported for a signed integer, that might be very closely related to the word size on your system, and maybe an underlying 2's complement representation for integers on your system. Or when you're looking at character sets, if there's a kind of byte-focused, ASCII-focused idea behind the scenes, then that's going to be very different than if you're taking a Unicode-based approach to character sets that are much more generic. That the data types that you're working with have both this abstracted idea of your data types and possibly also this very real tie to some hidden implementation, right, that has an impact on you as a developer and certainly has an impact on you as a compiler writer. Then you've got issues in terms of how you actually perform type checking and what you consider equivalent types. Are two things equivalent, type compatible if you like, just because they've got the same underlying data types? Are two things the same or compatible types just because they're both floats, or because they're both a struct that consists of an int and a float? Or do they actually have to have the same type name? So lots of languages allow user-defined data types. If I define a data type named temperature that is basically just a name for real numbers, and I define a data type named speed that's also going to be a real number, should those be treated as type compatible? Because under the hood, they're both real numbers. Or should we treat them as incompatible because one of them's a temperature and one of them's a speed? They have different type names, therefore I want them treated as different data types. So this idea of named equivalence versus structural equivalence is fairly important when it comes to the compiler side of things. Well, obviously from the language user, the programmer point of view as well. But these are things that we're going to want to come back and address. So we looked at how our context-free grammar can enforce the order of operations that we're using and the associativity of our operators. Is multiplication higher precedence than addition? Do assignment statements go right to left or left to right? What is the associativity of our operators? What's the precedence of our operators? So if that's defined from our context-free grammar, then what can we do in terms of our type checking if we want to make sure that operations are being performed on appropriate data types? So if you think about our parse tree as kind of giving you this top-down description of what an expression is made of, for instance, then at the very bottom of the tree we've got the tokens that make it up, right? The variable names, the numeric literals, and the actual operators that make this thing up. So if you've got, x equals 10 plus b times 0.5, right, that might be the token level view of our expression. And at the top level of this parse tree, you've just got this kind of generic expression non-terminal. Well, again, those context-free grammar rules describe what order the operations are happening in. So let's assume for the moment that our parse tree says that we've got at the top level an assignment statement that's got a variable is assigned and then some expression, and that expression is made up of an addition operator working on our numeric value 10 off on this side and an expression on the right-hand side, for instance, and that one in turn has a multiplication operator and its two operands are a variable and a real number. So you've got this tree expressing the meaning, if you like, structurally of that particular expression. So we build the tree maybe top down if we're thinking in a just basic recursive descent approach. But when we go through to figure out whether things are actually type compatible or not, we'll wind up working from the bottom up. Because we're looking, we're starting from things like the x, which presumably is a variable, and we can look it up in the symbol table. What data type is x supposed to have? We see the integer value 10 and go, okay, we've got an integer to work with there. We see the symbol b and look it up in the symbol table. We see the real number 0.5 and go, okay, we've got a token for a 0.5 there. And then we start working our way up the tree, right? We look at that from the bottom layer there, we look at the product of b and 0.5 and say, okay, I've got a multiplication operation on whatever type we looked up for b and a real number. So maybe I decide that those are real number operations, and I decide that the result of a product involving reals is going to be a real. So I decide that this expression has got a data type of real. And I move one layer up the chain. And I say now I've got an addition operation on an integer and a real. And so I say, okay, well, what's the result of that supposed to be? Maybe I decide that int plus real should give me a real. So I do the computation, or perhaps I do an implicit conversion and say, okay, well, let's convert 10 to a real first and then do real number addition. So I convert 10 to 10.0 and then carry this out and get my result, and I decide that also needs to be a real. So you work your way from the bottom up, deciding what, based on your operand types and your operation types, what should the result be? Maybe the top layer here I get to an assignment where I look at the data type for my expression that I decided was going to be a real, and I look at the data type for my variable, and who knows, maybe that's an integer. And so maybe at this point it's got to turn around and say, oops, now I've got to convert that real back to an integer before I splash it in there. And maybe I put out a warning about a narrowing conversion on that. But again, our compiler is going through from the bottom up in our parse tree, evaluating the data types, checking them to make sure they're of the appropriate types for one another and for the operation that we're working on right now. Now, it could also be that having that knowledge going through that process allows us to do some optimization as we're going through. You think about the sequence of operations for this particular beastie where we've got x's assigned 3 times 5 plus 17. Again, if we work from the bottom up and we see that, okay, I've got an int times an int. I actually have literal values for both of these. Maybe instead of keeping this as an expression, you say, well, I'm going to treat that as the integer value 15, right, as a literal 15. And then you see at the next layer up your tree, you see that literal 15 plus a literal 17. You go, oh, well, gee, I don't need to keep that as an expression. I'm just going to keep that as a literal 32. And so you wind up replacing this entire expression with a value that you compute at compile time and wind up saying, okay, well, I'm just going to assign 32 to x. So again, having the knowledge that you acquire as you're working your way up the parse tree allows you to perform certain optimizations as well. And again, we'll come back and look at this when we talk about code generation. But these kinds of operations, these kinds of optimizations, I can perform possibly directly in the parse tree before I ever even consider generating the code in my target language. Now, if we're looking at data types, we might also consider what we want to check at compile time and what we're able to check at compile time versus what I have to or want to check at runtime. So if I've got a statically typed language where I'm going to require everybody to declare all their variables in advance and they've got to give a data type for all of them, and parameters all have to be given types, and the return types for functions have to be specified. So if I go through and specify that everything that has to have a type associated with it, then I can go through and check all of that at compile time. I can check all of the expressions, right, because all of the expressions are going to be based on function calls and variables and literal values. So I can check every expression at compile time to make sure that the data types are valid for the operations that are being performed. And I know that during execution, only valid data types are being used, right? All of the operations have valid types. I don't have to worry about that at runtime. On the other hand, if I've got a dynamically typed language, or at least portions of it are dynamically typed, then I can't be certain what data type something's going to have at compile time. I can't do compile time checking. If I do something like, say, read a value into x and then multiply x by y, I can't be sure that x is going to have an appropriate data type for my multiplication operation. So at that point, you're also going to worry about, well, should my compiler be going through and inserting code to do runtime checking on x before the operation takes place? So where that x times y exists, should it be inserting runtime checks for x there? Or should it just say, if the programmer wants to use runtime checks, they can put their own runtime checks in. If they don't, then we'll just let it crash when it runs. And again, either approach is perfectly valid. It's just what the language expects and what users of the language expect. But it is something that we have to be aware of when we're going through and making that decision in our handling of our parse tree. We're working our way up this. And again, we'll come back and talk about that in the code generation side of life. Now, earlier I mentioned the idea of name versus structural equivalence for data types. If you've got two things that are both ints, then maybe you think that they should both be equivalent no matter what. They should be type equivalent. So if I go through and have some user-defined data types where the user can say, well, my temperature is just a type name for things that under the hood are going to be real numbers. Or they decide that, again, a speed is going to be a type name for things that under the hood are real numbers. It's entirely possible that as a developer, if I have a variable x that's a temperature and a variable y that's a speed, then as far as I'm concerned, you shouldn't be able to assign a speed to a temperature. So you shouldn't be able to do, x is assigned y, or vice versa. Or you shouldn't be able to take the product of a temperature times a speed. So in those cases, you're interested in having named type equivalents, where if they've got different names, then they're different types, even if structurally they're the same under the hood. Or the flip side is where we go for structural equivalence, whereas I don't care what they're named as long as they're structurally the same. If I've got two things that are both the exact same data type, they're both floats, or they're both structures that are composed of the same other structures, this equivalent structures. So if I've got a struct that's a float and an int, then I don't care what it's called as long as the thing I'm working with is also a struct that's a float and an int. So structural equivalence versus named equivalence. Named equivalence is easy from the compiler's point of view because you just compare the two names and say yes or no, yay or nay, and it's easy. Right? You've got greater compile time enforcement for abstract types. Again, you're preventing them from mixing and matching temperatures and speeds, for instance, and type checking is way easier. But structural equivalence gives the developer a lot more freedom in terms of mixing and matching things that are different named types, but allowing implicit type conversions between them. You know, if for some reason I do want to be able to multiply a temperature by a speed, then maybe it makes sense, or to multiply, you know, mass by acceleration, or whatever it happens to be. Maybe I do want to be able to mix and match those data types and just work off of the structural equivalence. So this is, again, something that we want to think about based on the desires of the language. What should our compiler do? And then we've got to have some kind of set of inference rules, some set of rules that tell us how things should behave. If I multiply an int by a float, what should the result be? If I assign a float to an int, what should happen? And so based on whatever the inference rules are for every operator, for the different kinds of operands it can work on, there should be some specification of what the result has to be. So maybe we decide that if I have an int multiplied by a real, then the way it's supposed to work is we'll take the real equivalent of that integer, multiply those two together, and get a real result. Or maybe we'll decide that if I've got, you know, so that's for the multiplication operation. Maybe for the assignment operation, I decide that if you assign a float to an int, then we're going to truncate it. Or maybe you decide that we're going to round it. Or maybe you decide that we're not going to allow it. But there should be some set of rules that specify what should take place, right? In each of these possibilities, what's the right one? So we're going to have, hopefully, some set of rules that tell us what the right thing for our compiler is, right? What is the right thing to do? And all of that's going to have to be supported. All right, and again, for a lot of this, we've gone through and dealt with it from a Yak perspective in, you know, labs 2, 3, or 4 this term. Okay, we'll pick it up with a few more ideas next time around.